and good day, Algebra. We are going over math packet number 4, tips and tricks that will help you make it through. This is due December 1st. The end of the try is December 3rd. There's not a lot of cushion if you miss that due date. There are some of you, I'm still waiting for packets 1, 2, and 3. Usually I knock off points for it being late. I'm being a little more lenient with people being in and out and things like that. If it's math packet number 1, you'll still lose points for turning it in late, but not as many. But anyway, so December 1st is the due date for this, Tuesday the 1st. So the first logic question here, a drop of water drips from a leaky faucet every 8 seconds. It takes 6 drops to make a milliliter. And the question is, how many liters drip from the faucet in a week's time? So there are 2 conversions here that you have to work yourself through. You've got milliliters to liters, which, does anyone know what the relationship 1 liter equals how many milliliters? Emphasis on the milli. That's a prefix.
Million.
No, not million.
1,000.
1,000. Okay. So that one's kind of easy. There's a direct conversion there. And then you also have to get from seconds to a week. Okay. And I'm going to get this kind of started for you, get you in the right mindset to convert seconds to a week. You may already know how to, but since you need to explain why your answer makes sense, you have to show me some sort of work. If this is the way you want to show it, then that works out well. So basically, seconds to week, we first want to start with minutes, then work up to hours, and then days, and then eventually to weeks. So we know that there are 60 seconds in 1 minute, yes? Our next unit up would be hours, which is 60 minutes. And you can either use cross products to solve this proportion, right? 60 seconds equals 60 seconds to 1 minute equals how many seconds to 60 minutes? Or you can use a scale factor. To get from 1 to 60, we multiply that by 60, so we're going to do the same thing with our 60 seconds. And 60 times 60 is 3,600. Right? So in 60 minutes, you've got 3,600 seconds. Now, the reason why we went to 60 minutes is because that's equal to 1 hour. So I'm just going to rewrite this same fraction, only instead of 60 minutes, write 1 hour. Because how many hours am I going to get to next? What's my next kind of conversion here? 24 hours, because 24 hours in a day, right? So if there are 3,600 seconds in 1 hour, how many seconds are there in 24 hours? Okay, multiply by 24. Again, equivalent fractions, scale factor. And what is 3,600 times 24, Lauren? 86,400. Right? So there are 86,400 seconds in 24 hours, which is significant because that means there are 86,400 seconds in 1 day. And you're only 1 step away from getting to a week, and you can finish that up. Right? So once you get the number of seconds in a week, then you go back to the situation here, and it says that a drop of water drips every 8 seconds. So how many seconds in a week? If a drop drips every 8 seconds, how many drops will that be? 6 of them make a milliliter. So how many milliliters will there be? And then convert that to liters. And that's ultimately the answer that I want on that line there. Yes? Sure. Okay? So that should be a more than generous start. We've only done about half the work, actually, because then you got to go back and calculate the every 8 seconds, 6 drops, and things like that. But to get from those seconds to week, that should get you going. Questions on that? Soybe. That's what I would do. So I'd be asked to get to 1 week. Wouldn't you multiply that 86,400 by 7? And if I were doing it, that would be my next step. Yes. Okay. The next one, I think the geometry people will appreciate a little bit more because it's kind of that logical thinking that we've been talking about with proofs. But you've got 4 sisters, Tina, Nora, Rita, and Maggie. And one of them's naughty because one of them drew on the wall of their room. And as a parent, it's now mom's job to figure out who the culprit was, right? So when mom saw the wall, she asked who drew on it. Rita said that Tina did it. Nora said that Rita did it. Tina said that Rita did it, probably because Rita said that Tina did it. And Maggie simply says, I didn't do it. But if only one of the girls is telling the truth, who did it? Okay? So you approach this knowing that one girl is telling the truth, which means the other 3 are liars. Okay? And there you go. there's no equation to set up here. There's no variable to solve for here. It's simply working through some of the possible scenarios here. What I recommend that you start with is, assume that one of the girls is telling the truth. Maybe you want to start and assume that Tina is telling the truth, which means that the other 3 are all lying. Okay? If Tina is telling the truth, then does that get you down to the person who drew on the wall? Okay. Someone said that means that Nora is also telling the truth. Why? There you go. If Tina's telling the truth, that means that Rita did it, but then Nora pipes up and she says, yeah, Rita did it. That means that 2 girls are telling the truth. That can't be the case. Only one girl is telling the truth. So right there, we've just eliminated Tina as the girl who's telling the truth. Not as the girl who wrote on the wall. She's still a possible culprit, but we know that she's not the one telling the truth. Okay? So kind of that logical thinking there, kind of working through each situation, teaching you how to be parents, right? Wading through the truth and the lies and figuring out the bottom of the situation. Yeah?
What would we write for one?
So while your answer makes sense, kind of explain your thought process here. The person, once you find out the girl that's telling the truth, kind of explain how that led you to the person who did it. If you write there, because I tested every situation, well, okay, but how did that get you to the answer? So basically, what was your thought process? This is more of like a written answer here, more paragraph form than just pointing to an equation. But anything else for that one? Okay. 5-card challenge. Similar to the other 5-card challenges that you've had, make sure that as algebra students, you are using an equation with all 5 cards. This one, in the spirit of Christmas, is about as opportunistic a set of 5 cards as you'll ever have.
Yes.
Why, Thumper?
Because we have a 1 and 2 4.
You have a 1 that's here for you, and you can make another 1 by using the division property of something divided by itself. You can also make a 0 with those two 4s, which might be helpful as well. Okay, so points aplenty. I should raise your limit to 50, I think. Points aplenty here. Okay. I don't think there's much more I need to say about this. We're all good. Okay. All right. Next page, we have the equivalent expressions. And in this case, I give you an equation, which is topical, considering we just took our test on kind of a deep dive into equations and different ways to write them and simplifying and things like that. So the given equation is 3x plus 2 equals 23. You need to tell me how many of those 5 equations are equivalent to that. Like saying the same thing, but just a different way. Okay? Is 2 plus 3x equal to 23? If 3x plus 2 equals 23, is 2 plus 3x also equal to 23? Yay or nay, and why? Yay, why? That's a good start. Very good start. Who wants to dive off of that one?
Oh,
Yeah,
because they're just switched around.
right. Because of the commutative property, things can be added in any order. If all I do is rearrange my 3x plus 2 to be 2 plus 3x, it's going to be the same thing, right? Just like 5 plus 7 and 7 plus 5 both equal 12. So if you can't think of the commutative property as the reason why, you could say, well, you just reverse the order, or the order with addition doesn't matter, or things like that. Okay. Questions on that one? Okay. On to the next. We have the area of the shaded region here. We've got 3 circles, 2 white circles inside of the larger circle, and the shaded area is that gray section, the space around the 2 enclosed circles. So we better know the formula for the area of a circle here, which by now hopefully it's becoming more and more recallable. You're able to memorize it. Who's got it? Pi times the radius squared. And so similar to other shaded area questions that we've had, this one will probably benefit you best to find the area of the entire circle, that large circle, and subtract the areas of the 2 white circles. Because if you start with the area of the whole thing and you take away the part you don't want, the unshaded part, you're left with the shaded. Okay. Just make sure, and this is starting to pop up on packets that I've been correcting. Some of you are finding the area of these circles and then writing that area down as the shaded region. No, if you find the area of these circles, you found the unshaded section. You want to subtract that from the whole so that you're left with the shaded part. Okay. Questions on that one? All right, going on to the next one, which I think you'll be proud of me. Look what I figured out how to do. Scan in color.
Yay.
I finally made it to the 1950s in technology here. Okay? Scan in color. So like other patterns we've seen, we're adding a color successively. Okay? We start with a single block and add a layer and another layer and so on. Packet 3, our shapes were triangles. Now in packet 4, we're dealing with rectangles. Right? And what? Rectangles, right. Like this entire shape here is a rectangle versus in the last packet, it was more of a triangle shape. Okay? So we can look at our first 4 figures here. And in figure 1, there's 1 blue block, no green, no red, for a total of 1. Figure 2, we still have our same blue block there, and we're adding 5 green ones, no red, total of 6. Figure 3, 1 blue, 5 green. Now we add, looks like 9 red, for a total of 15. Figure 4, I don't feel like counting all those blue blocks. How could I?
14.
Oh, okay. Yes, 14 blue blocks. Still 5 green, still 9 red for a total of 28. Okay. With the triangle pattern that we also saw here, it's going to be to our benefit to try and crack that code first, the total blocks here, which I was trying to get to with the last one, especially since we know that only 1 color is being added each time. If we didn't want to count those 14 blue ones, but we knew there were 28 total, 9 of which are red, 5 of which are green, then we could get to that 14 with subtraction rather than having to count them up. So, can anybody tell me some sort of pattern or some sort of something that they see with that total block column? Brady.
So for the figures, so it goes 1, times 1, and then it goes up 2. So you see 2 times 3 is 6, and then it goes up 2, and then 3 times 5 is 15, and then it goes up 2. 4 times 7 is 20.
So the area of a rectangle, of course, that definition tells you how many 1 by 1 squares can fit inside of it. And so what Brady's saying here in a little bit different way is that the height of each of these figures as we go up increases by 1. 1, height of 2, height of 3, and height of 4, right? So we can predict that figure 5 will have a height of 5. That seems to make sense. Follow that pattern there. And the base, that length, we start with a 1 by 1, then it jumps up 2 to 3, then up 2 again to 5, then up 2 again to 7. So figure 5, we can predict will have a length of 9, which gives us a total block of 45. 5 times 9. Everybody see that there? The height is increasing by 1 from figure to figure. The length is increasing by 2. Okay? And the fact that we know the total blocks being 45, how is that helpful? Because we know the next color added is going to be green. I don't want to draw that figure. 45 is a lot of blocks to draw, and then you have to color them all in. And how is that 45 helpful? How many blue blocks will be in figure 5? 14. And we know that because only one color is added at a time. And if it's green's turn, that means that blue is staying the same and red is staying the same. So far, of those 45 blocks, 23 of them, 14 plus 9, are already accounted for, which means how many are going to be green? 22. Okay? Let's look at figure 6. What will the height and length be of figure 6? Bridget? The height's going to be 6. And Brent?
11 gonna be
The length is going to be 11. Again, up by 1 for the height, up by 2 for the length, which gives us a total block count of 6 times 11, or 66. Whose turn is it to change, or whose turn is it to add here? Red. So green, so blue isn't changing. Green isn't changing. I've got 36 of my 66 blocks accounted for. That means there are going to be 30 red. So one thing that we're doing here with these pattern block questions is finding that pattern to predict future results, so we don't have to actually draw out, or there's some calculation here, but it's relatively basic calculation once you kind of get that pattern going. So for algebra, your job is to complete the table. And geometry, we'll talk about your packet next week, but you get to make another graph. The graphs, by the way, just get cooler as you go through them. Any questions on this one? Okay. Next up, we have surface area, and I incorrectly named this. This is not a right rectangular pyramid. It's just a pyramid. Your volume question is a right rectangular pyramid. I just copy and pasted to this page, and that was foolish because, whatever. But it is a pyramid, and your job is to find the surface area and draw that net. There are several people who are losing points on this page. They're not drawing the net or not labeling the net. So this is an important part. Okay. What shapes make up this three-dimensional figure? If you were to unfold it, lay it flat, what shapes would be in it? Soybe? Square as our base, and then 4 triangles coming from that. And then we have to label each side. The fact that the base is a square tells us that they're all 8. And why is that 16 value a dotted line in the middle of that triangle? Why don't they just put it, on the outside here if that's 16? Elise?
Because it's the height of the rectangle in, so it goes on the side and then the height.
Right. The diagonal side of that triangle is not 16. Okay. The height of the triangle is 16, which is a good thing. That's what they give you because that's what you need to find the area of a triangle. For the area of a triangle, we don't care what these sides are because we don't use them. Right? Base times height divided by 2, area of a triangle. So we've got the base and we've got the height there. Questions on this one? Okay. Then we go to volume, and this is a right rectangular pyramid. Anyone know the formula for the volume of a right rectangular pyramid? You'll recognize when I start to write it, it starts out with base times width times height. What do we know that's a formula for? The volume of a cube or a rectangular prism. It turns out that a pyramid is 1/3 the volume of a rectangular prism with the same dimensions for base, width, and height. Okay, so if we were to kind of take this shape and draw a rectangular prism around it that would have come from, the pyramid's 1/3 the volume of the original rectangular prism. So it's base times width times height divided by 3. So for this particular pyramid, the base being 10, the width being 8, and the height being 6, we divide that by 3 to get 480 divided by 3 or 48 divided by 3 and tack the 0 back on? Anybody? 160. 160 cubic inches for the volume. For algebra, your question here says, what is the volume of a right rectangular pyramid taken from a rectangular prism with base dimensions of 16 and 28 feet and a height of 14 feet? So what I'm looking for here is giving you the dimensions of the rectangular prism. Uh-oh. Does that work? That's not too bad. What would the volume of a pyramid taken from that be? Cut out of that be. And it goes back to the relationship between the formulas for a rectangular prism and then a pyramid. Okay. Questions on that? Okay. The next one, if I think I know what's coming, I'm super excited to tell you. Yes. Yes. All right. So we talked about last packet that Pascal's triangle has that whole Plinko relationship where it's the number of paths to the top from any given element here. Today we're going to talk about Pascal's triangle in relationship with probability because this is awesome. Okay. So one usage of Pascal's triangle is to determine probability. Consider me flipping 4 coins. Okay? You win if you get at least 3 heads or 3 tails. And the question here is, what is the probability that you win the game? And first, to kind of set this all up, let's consider all possible results. Next to each result, write all possible combinations of that result. So how many ways are there, flipping 4 coins, to get 4 heads and 0 tails? Just one way, right? Getting 4 heads and no tails is the only way for that outcome to happen. How many ways are there to get 3 heads and 1 tails? 4, right? Because it depends on when that tails pops up. You could get the 3 heads first and then the tails. You could get 2 heads and then the tails and then your 3rd heads. You could get 1 heads, then the tail, then 2 heads. Or that tail might come up first. and then the 3 heads after that. It is. Okay, but those are the 4 possible ways to get the combination of 3 heads and 1 tail. This one you might want to write a little bit smaller for, okay? But for 2 heads and 2 tails, what are all the possible ways for that to happen? Well, we could get 2 heads right off the bat, and then 2 tails. Or maybe we get 1 heads, and then a tails, and then a heads, and then a tails. Or maybe we get a heads, and then a tails, then a tails, then a heads. I think that's all the possible ways for getting a heads first. Elise? Okay. If the tails comes first, we could get 2 tails and 2 heads. Or a tails, a heads, a tails, a heads. Or a tails, a heads, and a tails. If anyone can think of another way to get 2 of each, let me know, but I think that covers it. 1 heads and 3 tails. What is that one going to be very similar to? The second one, right? Getting 3 heads and 1 tails is kind of just the reverse of getting 1 heads and 3 tails. You know, we could get our 3 tails first and then the heads, or 2 tails and then a heads, then the other tails, or 1 tails and then the heads, and then 2 tails, or maybe that heads pops up first, and we get 3 tails after that. And how about the 0 heads and 4 tails? How many possible ways are there to get 0 heads and 4 tails? Just 1. Tails, 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 tails. Anyone see where I'm going with this?
Yeah.
What is it? Gabby?
It goes from 1 possibility to 4 possibilities to 6 and 4 and then 1.
It goes from 1 possibility to 4 possibilities to 6, and then 4, and then 1 again. Where do you see that very thing in Pascal's triangle?
That's what we're trying to
I'll pause for a moment while you gasp in amazement. Hey, look at that.
Wait, then the next
Again, just this pattern of simple addition brought us not only what we talked about in packet 3 with the whole number of paths thing, but this piece also. Okay, so now back to the original question, because in order to calculate probability, what do you need? You need successful outcomes and possible outcomes, right? That's what probability is, success over possible. So is it a successful outcome for, if your goal is to get at least 3 heads or 3 tails, is 4 heads and 0 tails a win for you? Yes. How about 3 heads and 1 tail? Yes, at least 3, right? That includes 3. 2 of each?
No.
No. 1 head and 3 tails?
No.
Yes.
Oh.
Okay, because at least 3 heads or tails. And then obviously getting 4 tails would be a win as well. So knowing how many outcomes there are for each situation allows you to quickly, if you know where to look in Pascal's triangle, quickly identify how many are successful, 10, and how many are possible, 16. So you have a 10 out of 16 chance of getting at least 3 heads or 3 tails. You actually are favored to win here. If you want to write that as a percentage, it's approximately 63% chance. Okay. Good stuff, huh?
No.
Come on, this is cool. Like, think if you had been the one to find Pascal's triangle, you know? Sorrentino's triangle. Wouldn't you want people to think this is neat?
Yeah, and then you have a homework assignment, and then
There
Trey
you
goes
go.
to make that triangle. Yeah.
Last algebra class started calling this Karen's triangle. I did not find that very humorous, but yeah. So the next one here. Write all combinations for results when flipping 5 coins. So same type of situation that we have up here. And then with 5 coins, look at the number of ways to get each result. Can you predict, without writing all the combinations, what the number of combinations are going to be? Thumper? 1, 5, 10, 10, 5, 1. How do you know where to look for that? Like, why is it not 1, 8, 28, 56, 70, 56, 28, 8, 1? Okay. Also, Daniel?
Because if you're flipping, when you flip 4 coins, you were in the row of 5, and now you're flipping 5 coins.
Right. 4 coins, you're in row 4. 5 coins, you're in row 5. So when you get to these questions over here, where it says flipping 7 coins, how many ways can you get exactly 4 heads and 3 tails? Your answer to that is going to come from row 7. Okay, because you're flipping 7 coins. Is this brilliant?
No.
Well,
It's a pain to do it,
but it's cool.
It's just too much work.
Cool for old people. Yikes. Okay. Other questions on this one? Okay. Elise, is that a hand up? No? All right. Next question. They got to get better from here, right?
Actually, the block ones are shit.
That's true. Probability, again, the possibility diagram number 2. This section here, describing how to make the possibility diagram, hasn't changed since the last time that you saw it in packet number 2. So it's just kind of what the possibility diagram tells us, right? It tells us how many outcomes for each situation. The reason why it's got 6 and 6 here is because we're rolling 2 6-sided dice. So 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and then all the possibilities for what sums you could get, as an example there. In algebra, you've got 2 spinners, each with 8 equally sized sections. Using a possibility diagram, what is the probability of spinning the same number both times or a product that is less than 40? That or does not mean you get to pick which situation. It's not 2 different situations. It's the same situation. It's kind of like an or statement in the sense that there are 2 things going on at the same time here, or two avenues for success perhaps. But we need to remember to not count a successful outcome more than one. So getting your probability diagram or your possibility diagram started, how far will my x-axis go out here? 8. Why? Because our spinner has 8 sections on it. And we'll mark those 1, 2, 3, 4, 5, 6, 7, and 8. Same thing going up, right? My other spinner also has 8 sections on it. So 1, 2, 3, 4. Oh, I can do that better. I want to space them out a little bit more. Yes, perfection, always. Okay, 1, 2, 3, 4, 5, 6, 7, and 8. And so the question is, obviously we are finding, products here, the same number both times. We care about that. That's successful. Or a product less than 40. Product means what operation? We're multiplying here, right? So when we go through this, we want to multiply. 1 and 1 is 1. 1 times 2 is 2. We can just kind of go up the line here. 3, 4, 5, 6, and 1 times 8 is 8. We can kind of do the same thing going across here. 1 times 3, 1 times 4. Write these products in here, 7 and 8. 2 times 2 gives us 4. 2 times 3 is 6. Kind of going up by 2's here. And we can fill in the next horizontal as well. 2 times 3 is 6. 8, 10, 12, 14, 16. So we can fill out like that. Okay. And our successful outcomes here are the same number both times, or products less than 40. So when I look at this, the reason why I said not to count a successful outcome more than once, give me an example of a successful outcome that falls under both of those categories. The same number both times, which is also a product less than 40. Elise?
The 4.
In the 2 times 2?
Yeah.
Yeah. So this one here is kind of a successful outcome to both of them, right? It's the same number both times, 2 times 2, and it's a product that's less than 40. Turns out 1 times 1 gives us the same thing, also a successful outcome to both situations. So what you don't want to do is count the same number both times and the products less than 40 separately, and then put them together. Because when you do that, then you'll have the overlap and things counted twice. Okay? If I only circle that 4 once, representing it both as the same number and a product less than 40, I'm only going to count it once. Okay? So do the whole thing together and count each outcome as a successful outcome only one time. Don't do it separately and combine them, because that's when you'll count them twice. Does that make sense? Okay? All right. Some of you look like I just broke your brains or something. But brains rejuvenate. You'll be fine. You will be fine. Okay? And the last page is your polyomino. I tried to make a T, but couldn't quite figure it out. As with anything with these pieces, you can definitely use logic to help you set this up. For example, what's that? You finished it? Good. And you might have used the fact that a shape like this, or a shape like this, or a shape like this aren't going to show up anywhere in the stem part of that T, right? Until you get down to the bottom here, because that stem part is only 2 blocks wide, and all 3 of these are 3 blocks wide, right? So neither of those shapes can possibly be in that section of the T. So you can kind of use that to help you. You know, this one here, which is 3 blocks tall, and this one here, which is 4 blocks tall, 3 blocks tall here. Those aren't going to show up in the top bar unless they're, in that section there, perhaps. But use those kind of bits and pieces to help you place some of them, and you can go to town on that. All right. With 2 minutes to spare, that wraps up packet number 4. Any questions, comments, concerns, complaints, compliments, congratulations, or criticisms? Yes.
So on the 5-card challenge thing, there's 2 4s. Can you have the same equation twice?
No, that's a good question. So back to the 5-card challenge. Since you have 2 4s to use, and you have a 1, right, to make a 3, you can't say 4 minus 1 equals 3, and then your next equation be 4 minus 1 equals 3, and say, well, I used the other 4. It doesn't work like that. Okay. You can use both 4s in the same equation, but you can't write the same equation and say I used the other one. That doesn't count. Yeah.
I have a question.
Yes.
Are we ever going to use this in the real world?
Will you ever use this in the real world?
Any of this. Video games.
Yes, you will. I have a million examples of practical application of this in the real world, but we're out of time. So I guess we just got to wrap up the video. And Bridget's really raising her hand high. Yeah, go ahead.
So this is like a complaint.
A complaint. Ooh.
Yeah.
Whoa.
So
Should I turn off the
does this
recording?
have to
Oh.
do anything with like what we're actually learning?
So,
here? Like this is like it doesn't correlate.
yes.
Only this
Yep.
one is small.
Oh,
and the
Okay. So the math packets are not directly tied to the curriculum that we're doing currently from the binder. That's why this stuff doesn't show up on the test. However, this is the critical thinking, problem solving, math extension type of thinking. You do not want to go to high school in math just knowing opposite operations and slow burn subform and things like that. You want to know how to apply those things, when to use those things. You want to be critical thinking problem solvers. Okay? Every invention that we've had is an invention. It's new because someone thought, what if I did this differently? You know, what if I try this instead? Those are the kinds of thinkers that I want you to become. Now we really are out of time, so we got to go. Due December 1st, that's how you math. Don't forget to like and subscribe. I got to escape first, and then